Can I share now? Yeah.
Okay, we see your screen. Please.
Okay. Just little bit to talk with Professor Juan Martinez, my close friend. A long year ago, we have some visit and invite Professor Juan to our lab. We have discussion about many problems. Also, we send some students. These are just written is some workshop at Fig Point, can do Fig Point and Canada. The first picture is Canada. Very beautiful mountain. Also in Thailand. Every year I send all students to visit him. And now student candidates, Dr. Tavisha with him. Also we invite lecture always. Is some memory. It's very nice. I think it's next year we can travel. I will visit him. So thank you very much for your accept for talk of this event. Thank you very much, Professor Juan. Okay, maybe that's all.
Okay, thanks for the introduction. And next, I would like to invite Professor Juan Martinez Moreno to give his talk.
Thank you.
All right, so you have 45 minutes. Can you share your screen?
Sorry. What is the? Yes, but I cannot find the place. I use
in below bottom for share screen.
Sorry, I have a problem with saying my screen. Pardon, sorry, but I cannot find the how I can share
Oh. Do you mean you don't have the share button?
Yes, I don't see.
Oh. Okay, I don't know how to help.
Maybe Juan can send by mail the file to you, and you'll share the screen, and Juan will speak about.
Will you send the PDF
by email? Send my email. Can I
send you the PDF by mail, and Parin will make the share. But Juan, do you see it's a green button usually on the green?
It's underneath the window.
Not in
just
my computer.
On the bottom of this screen.
Maybe because I not installed the Zoom. I am
okay. It is possible.
Maybe
you did not install the Zoom. Okay, then I can understand.
Then please send me the file. I will share.
Yes. Okay.
The screen for you, and you talk. กรวุฒิแชร์ให้หน่อยได้ไหมครับกรวุฒิอยู่ไหน
ได้ครับ
กรวุฒิ
Now,
could you help
I
me
think
with-
that you have in your computer.
Hello, my Perker. How are you?
Thank you, Professor. I am fine. And you? I am happy to
Okay.
see you.
Hello, hello.
Hello.
Nice to see you.
It's also for me.
Okay. Let's hope we'll have the opportunity in the coming years to meet in person again.
I hope so. I hope so.
Now we are limited just to this kind of online meetings.
Yes, that's true.
From the point of view of the conference, it is quite all right, but for the social
Yeah,
part of the,
yeah.
is not complete.
Yeah.
it's
where ภาควิชา professor
it's such a pity that we
ภาค
cannot
วิชา can help you
make discussions during this kind of event.
Sorry. I wanted
Sorry.
to feel the time.
Have you the file?
Yeah, I got the file. I'm downloading it. Okay.
โอ้ภาควิชา where are you you not near professor room for help ภาควิชา
Everyone can see the screen.
Okay, I can see. Thank you.
Okay.
Okay.
Sorry
Thank
for
you
the
so much.
inconvenience, guys.
Sorry, because I am using the wet one, the wet Zoom, and I have not installed it in my computer. Maybe this is the reason. Okay, thank you very much for your invitation, Parim. Thank you very much. It's a pleasure for me to stay at this meeting at this moment. Thank you so much. I have to say that I have a very good collaboration with Bangkok team, but Professor Kuman team. I am very happy to be friend of Professor Kuman. I have a nice collaboration for many times, and I have always a student in my university. Nowadays, this year I received 2 students. Nowadays, there is 1 student, Pawicha, stay with me in the University of Jaén. I am very happy with the collaboration because I can study many problems with Professor Kuman and student. And I would like to receive Professor Kuman next year, maybe at the beginning of the year, for visit me again, because he's a very nice collaborator. Today I present a paper writing in collaboration with Gopal, Professor Dhananjay Gopal and Professor Nihat Osgur about the fits figure problem in this case in physimetric space. This is a new problem, a new category of problem in matrix fits point theory, and especially it's a problem of finding self-mapping which remain invariant at its point of, in this case, a circle in the space. This problem is recently introduced by Gur and Tas. We present and they introduce the problem in metric space, and we try to translate this problem to fuzzy metric space. Please, Parin, come on. New page. Okay, more or less, this is a thing of a table about the speaker. First of all, I am going to present Karisti theorem, well-known theorem, and this is a very short introduction. And later, I am going to talk about the problem of the field circle problem in the case of metric space, And later, I would like to translate to fuzzy matrix space, as I said you before. There are another problem that appear, changes the circle with another kind of figure. For example, for another curve, or for example, the Cassini curve problem, it's very similar to this one. New page, please. Thank you. A geometric and topological property of this point set have it extensively studied for various aspects in the fixed point theory. For example, after some years, Caristi present a well-known paper, about the existences of a phase point in this situation. If we have a complete matrix space, if T is a self-mapping of the matrix space, such as there exists a lower semi-continuous function satisfying this inequality, these inequalities, then Caristi's prove that T has a fixed point. This theorem is well known and also allowed to characterize this problem is equivalent to the Eclat variational principle. Here proved that matrix space is complete if and only if every Caristi mapping has a fixed point. Yes. New page. Yes. Some example of this Caristi mapping can be constructed from Banach and Canat mapping. If we start with Banach mapping and we consider bar phi this function, or we start from a Canat mapping and we construct this function, this phi function, in two cases, we have a Caristic mapping. This means that this T satisfied if T is a Banach of Cannon contraction. This T is also a Caristic mapping and satisfied the inequality. These are result of this author, Shioji, Shuzuki, Takakashi, and Petrucci. Yes, next. In other hand, task initiate the fixed circle problem in matrix space. Yes, exactly. They consider in a matrix space. They consider the circle. What is the circle? Circle is just the border of the ball. Yes. Yes, of course. This is R point belong to the metric space, such as the distance to a center is constant to R in this case. Yes. What is the problem of this circle? The problem is to try to find theorems, try to find conditions such as self-mapping T fixed circle point by point. This means that every point in the circle is a fixed point. Yes, is obviously is trivial than a circle with a radius equal to 0 is just a point. Then, in some sense, this theorem of this result can be a generalization of fixed point theorems. Yes, please. We start with an example. If we consider the matrix space defining in complex C, complex matrix space, where the matrix space is defined by equation 1. This is the definition defined for every pair of complex number, F1 and F2. Then we have a matrix space, as I say. We know that this matrix space is induced by the known writing below. Yes. Next, we can consider circle in this matrix space. For example, in the picture we can see the circle with center 0, 0, 0, of course, and radius 1. Yes. For the result, author and task define the phi function. This phi function is defined as the distance for a fixed point. For a fixed point, this is the distance between any point and the fixed point x0. And the first result, recently proved by author and that, asserts the existence of a fixed circle of T if the mapping satisfies two conditions, condition C1 and condition C2. Yes, condition C1 say that the distance between T point and its image is less than phi x minus phi tx. And the second one say that the distance between the more or less I have a slide for this. The second condition say that the distance between the center of the circle and the image of H is greater than R, and this is in a geometrical way. This means that TH is offside of the circle. Yes, it's in the exterior of the circle. Yes, please. Yes, condition C1, I have a picture more or less. Condition C1 say or guarantee that the point Tx is not in the exterior of the circle. If we have a point X in the border, just in the circle, yes, and we have the center, then the red line is in the first part of the inequality C1, and red and blue and green are the other part of the inequality. And this means more or less in this condition, this is just the reflection of this picture. Yes. Yes. Come on, next. Second condition is very easy, that guarantee that the point is not in the interior of the circle. Yes, if we collect one condition and second condition, we have, of course, that the image of every point in the circle, it's also in the circle. Moreover, the theorem say that the point is a fixed point, not only globally the circle go to the circle, but also is a fixed point. Yes. Next slide. Thank you. In the previous example, in the example of complex numbers, complex matrix space, if we consider this function, this is an example of the author and task paper. This function, this mapping, contains the fixed point f of T contains the circle C01. That is, C01 is a fixed circle of T. Therefore, the study of geometric property of fixed point set of a self-mapping seems to be an interesting problem in case where the fixed point is not unique. Yes, thank you. Later, Author and Tas, in the same paper, present different modification of the theorem, and they present a different condition similar to previous one that will guarantee the fixed point result, the fixed circle result. Yes, the first in this case they present C1 star and C2 star, two different conditions that just writing in the reverse order. What this mean? C1 guarantee that the TH is not in the interior of the circle, and now condition C2 guarantee that TH is not in the exterior of the circle. Yes, we have a very similar condition, and we have a very similar theorem and very similar proof. Yes, this is a variant of the previous one, and they present also a third one. Yes, third. Sorry, it's the same. Yes, they present a third one. Yes, this is the new condition C1, same condition. Sorry, C1 at the beginning, and second new condition C2 to start, where they use some 8 in 01. And this is another modification, as I said before, a very similar result. C1 guarantee that the point is in the interior of the circle, and second one guarantee that is in the exterior. Yes, at the same time, then together guarantee that it is exactly in the circle. Yes, please go. A new after this paper, there are some papers trying to reproduce a result in another context. That's author also and collaborator also try to do for F contraction. I remember the F contraction, very famous now kind of contraction, introduced recently by Wardowski. For this, Wardowski is present a family F function such that F1, F is strictly increasing, F2 for any sequence, this sequence converts to 0 if and only if the image of the sequence converges to minus infinite. The third condition, there is a constant k such that the limit of alpha kf alpha is equal to 0. This kind of function are auxiliary function for define the Wardowski contraction, now called F contraction. Some example of this kind of function is, for example, logarithm plus u, and other in the screen, please. Wardowski present the F contraction as a generalization that, as said, kind of for every pair of points such as Tx and Ty is bigger than 0, then this inequality has to be satisfied. This kind of contraction now, as I said, is called F contraction. As a generalization of Thur and Tas, define a little modification of this contraction and present the FC contraction in order to obtain a fixed circle theorem. This is the definition of this kind of contraction presented by author and Tas, where you can see that you replace some part of the element in the contraction. We know that in this case, the point x0 must be a fixed point of the mapping. This is guaranteed with the contracting condition of new contracting condition. Please, new slide, please. authorities proved recently in this year that if they have a contraction FC of the contraction of this kind with respect to X0 point, and they define the number sigma as an infimum of the distance, then the center the circle center in X0 and radius sigma is a fixed circle T. Yes, in particular, also we can prove that T fits every circle with radius less than sigma. Please. Yes. There are our result. Other author translate this problem to another context, to S metric, regular metrics, partial metric, and I think that in future many papers will try to introduce this problem in another context. Yes, please. Okay. We want to do more or less the same. We want to translate this problem to the fuzzy matrix space. Can we do a similar result for fuzzy matrix space? Can we do this? This is our proposal. The first, we need to define what is a fifth circle in the context of fuzzy matrix, and after that try to present result in this context. First of all, I'm going to introduce the fuzzy matrix space. Fuzzy, for it, I need a T-norm, a triangular norm. We are going to work with a continuous triangular norm. This is an operation in the interval 0, 1, a binary operation that satisfies condition 1, 2, 3, and 4. Condition 1, the operation star is commutative and associative. Condition 2 is continuous, it's a continuum mapping. Condition 3, 1 is 1 star A equal to A for every A. 1 is a unitary element, and 4 condition that this operation maintain the order of elements of 0, 1, please. Some basic example of T-norm are the minimum T-norm, the Hamacher class of T-norm defined by the 0 if A equal to V equal to lambda, and defined by this fraction, this operation otherwise. Also, the product is a T-norm, and the well-known Lukasiewicz T-norm defined by a max of 2 operations. Yes, T-norm is called Archimedean if satisfied that A star V greater than that A imply necessarily that B equal to 1. Yes, all these example of T-norm of the example present up at Archimedean, except the minimum 1. Yes, please. George Beramani introduced or present fuzzy matrix space. First of all, the first introduction of fuzzy matrix space is by Cramosil and Michaelet. But by Cramosil and Michaelet present this fuzzy matrix space but when you try to translate problem of Banach contraction to Cramosil and Michaelet, there are some problem. In order to solve this, George and Beramani introduced a little modification of Cramosil and Michaelet, a particular case of Cramosil and Michaelet, in order to improve this kind of sorry. Sorry. Yes, a factometric space in this sense and in this paper is order triple. Yes, where we have a set, we have a tenon, a continuous tenon, and we have a fuzzy set. This means a mapping from this x times 0 infinity, satisfying this condition. Condition GV1 say that n is always greater than 0 for t greater than 0. And second one say that 2 points are equal if and only if m is equal to 1 for all t greater than 0. The third condition is the commutative condition. Fourth condition is more or less the triangular condition. Is a similar triangle condition in metric space, similar to this case. And finally, the fifth condition is the set continuity of n of this function that you can see. Yes, please. New one. Example, there are many examples. There are papers with only there are some papers only for construct example of this kind. Yes, and this is classical example. There are two classical way to construct a factometric space from a metric space. If we have a metric space and we define and we use the product T-non, we can construct a factometric in this way. As I say, this is one of two natural way of construct. This is called standard factometric space induced by D. The other one is using the exponential. Yes, come on. More example are here. We have in the first example, also in two examples, we have the T-non product. We have two examples with the minimum and the maximum of two numbers. I have to say that the first of this is a stationary factometric space. What this mean? This means that this factometric space doesn't depend on t. It's constant for every t. This factometric has some advantage in front of classical metrics, especially in process of filtering in image. Some paper. This new one. New slide, please. Pari? Thank you. Okay. Of course, as you can imagine, all result in metric space can be translated or can into translate in fuzzy metric space. A fuzzy metric space characteristic result is present by Avasi in fuzzy metric space. For this result, Avasi need to use non-Archimedean or strong fuzzy metric space. Non-Archimedean or strong fuzzy metric space is a fuzzy metric space that satisfies a new, more restricted triangular condition. So that instead of t plus s, they satisfy the triangular condition for equal t. T is equal in the first n, in the second n, and in the third n. And he presents the theorem that is a similar theorem to a characteristic one. Yes. This is if we have a completely fuzzy metric space with a continuous and Archimedean T-non. Yes, T is a self-mapping if there exists a fuzzy function phi and upper semi-continuous function that satisfy this inequality. This inequality is similar in some sense that Caristi one. And in this case, T, Caristi assert that T has a fixed point in a fixed point, yes, in the fuzzy matrix space. Yes, please. Yes. Now we are going to present the circle problem, the fifth circle problem in fuzzy matrix space. What is a circle in fuzzy matrix space? A circle depends on T. Yes, we have in this slide we have two different circles. The first one is a T circle. I use in the paper not distinct the name. The circle, the same name for the two different circles. The first one, C, circle is a circle that the center point R is radius and D is a parameter. Yes, and this is the point that at that the nx, the distance between the x0 and x is equal to 1 minus r, meaning for every t, of course. And if this is true for all t, then we talk only of circle x0 radius r. Yes, if we consider an stationary metric, then the concepts are equal, because I remember that stationary means that the fuzzy matrix space is constant. Please come on. What is the problem that we try to solve? We try to find mapping T such that all point in circle is all point in circle are fixed point. Then we say that the circle is a fixed circle of T. We have two problems. The same problem for the first kind of circle, and second problem for the second kind of circle. Yes, also is similar problem. Yes, this is an example. This is an example of asymmetries defining but the previous kind, and we have a T. If we use this T, it's easy to verify that the mapping fits the circle as 1 radius 1 divided by 2 T. However, T does not fit this other circle. Also, the point is a fixed point of a mapping. This point is in the circle. Please, another slide. Yes, and this is our first result. This is the fifth circle result, the fifth circle theorem that guarantee that the existence of a fifth circle of T. If we consider the function phi T defining as the distance between x and x0, similar to that of 2 and that result, then we can consider two conditions, condition P1 and P2. And P1 and P2 are very similar conditions to the previous condition of 2 and 2. P1 guarantee that the point Tx is outside of, inside of, is not in the stereo of the circle, and the second one just the reverse. And combining this condition, we have a circle condition. If we see P1 condition is very similar to a fuzzy contraction, a fuzzy contractivity condition. Yes, please. Another one. Yes, we have two remarks here. We know that the fuzzy theorem guarantees the existence of fixed point, while our theorem guarantees the existence of a fixed circles. Yes, in the case where circle has only one element, a fuzzy theorem is a special case of fixed of our result. we have to be careful with this because our phi condition is defining in precise way and not in the case of a basic one. Yes. Second, condition P1 and condition P2 guarantee that the point is is not in the interior and is not in the exterior. Yes, in the similar way that previous result. And the converse of the theorem is true. Is also true because condition GB in the definition of asymmetric space. Please, new one. We have here an example. This is an example, an easy example. Yes, please. And another example. This example is interesting because we have an example where T defined in this way, yes, T fits two different circles. Yes, and we it's interesting now to ask about the uniqueness of the fifth circle. Please, we can ask about this. The following example show that the theorem is not true when we have the minimum T known. Yes, in the theorem we use the Archimedean T known, and as I said before, minimum is not Archimedean T known, and we have an example where so that this condition is important because example where with a T known where the theorem is not satisfied. Yes. And the T is free of this mapping. Yes, this is another example that illustrates the superiority of our result over a basic one. Yes, we consider this asymmetric space. And yes, continue. This is a definition, a precise definition of asymmetric space. Asymmetric space is a sequence of points, and we define using this T known, we have a precise definition of M. And this is, you can prove that this is a asymmetric space. Please continue. And if we consider T, this T satisfies all conditions of our fixed circle theory, and consequently T fits the circle C that I have here. However, T does not satisfy a basic condition. Then we have a example satisfying our result and satisfy that fits every point of a circle, but T doesn't satisfy a basic condition. Yes. Please, new one. Identities satisfy P1 and P2 condition, and identity satisfy our theorem trivially. Then it's necessary to eliminate, to exclude identity in our result. For this, we present a triangular asymmetric space, a special kind of triangularity of asymmetric space. This is very similar to a triangular asymmetric space well known in literature. And we have an example here of asymmetric space taking H equal to 2. Please, another one. Yes, as I say, we have now a result that characterizes the mapping T, characterizes the identity mapping. If we have a triangular asymmetric space, as before. And we have a new contracting condition, a new triangular contracting condition number 9. This T satisfy this contractivity if and only if T is equal to identity. Then phasymetry space, phasymetry space is called a triangular phase space with respect to T0 if H condition previous is satisfied only for T equal to T0. Yes, please. We know, to comment here, we know that if self-mapping T in our theorem does not satisfy condition A's, then T cannot be the identity mapping because this is a characterization. In our result, the fifth circle is not necessarily unique. Example before illustrate the situation. I fixed the attention in the point that we have a problem with two different circle fits circle. Yes, and we are going to present a unicity one. Yes, next. Yes, this is a uniqueness result. For uniqueness result privilege, we are going to introduce, use a C function. C is a continuous, not decreasing, and greater than T function. Yes. We have a phasymetric space with a T non-continuous and Archimedean, and we have also T mapping satisfying condition P1 and P2 in our main result. If we consider the contracted condition, this contracted condition very similar to behead condition, yes, but satisfied only for point X and Y in the circle and outside the circle. This condition is valid, is necessary only to check for point in the circle and outside the circle. Then in this case, the circle is unit fixed, is the unit fixed circle of T. Of course, this is valid for all T greater than 0. Then we have a condition that assert the uniqueness of the fifth circle of T. Yes, next. We have here an example that illustrates this. Yes, please, next one. I think I am on time. Yes. We can consider another different figure. We can consider not only circle, we can consider other kind of curve. This is the example of Cassini curve. We present Cassini curve. Cassini curve is the point that satisfy is the point in the phasymetric space, of course, that satisfy that the product of two distance is equal to 1 minus gamma, and this is a curve with that we can think or we can study similar property about the how mapping T fix this kind of curve. Yes, and in this way appear the problem of fixed Cassini curve problem. And what is this? Of course, this is to find condition such as T fits every point or in this curve. Yes, please, another. Yes, but we have a Cassini theorem. I said Cassini theorem because it's a theorem for this curve. We consider it's very similar to the previous one. We modify the definition of phi function in number 11. Number 11, we consider the phi function for every t, and if we change condition P1 and P2, but for new C1 and C2. And the proof and the situation is has a little modification from the previous one, and we have also a a result that say that the Cassini curve is just a fixed Cassini curve of T. And this problem, please, and another one. Is, we have here an example. Yes, this is an example, and it's easy to verify condition C1 of C2 of the theorem. And the set of fixed point of T is just the interval 1, 2, and the set of fixed point of Cassini curve is just the same. Is the same interval. Yes, you can check. Yes, next. Here is a general definition of Cassini curve for any endpoint. Yes, but the result is very similar. Please, two or three slides. Yes, but it's very, very similar. I want to present last this one. This is a new example for the Cassini, any dimensional Cassini curve, please, more. Yes. Third important problem. Third important problem is how can include more curve? How can introduce this problem for different figure? Chauha and collaborator established some nice result in cat-zero space. They prove that the fixed point set of a quasi non-expansive set mapping of a matrix space is always closed. Yes. They consider quasi non-expansive mapping, and they can prove that the fixed point set is closed. And this is a very interesting result.
Hello. It seems Professor Juan
I cannot hear. It's for all.
Yeah, I cannot hear too.
All right.
Maybe his internet connection have some problem.
Yes, I suppose, yes.
Okay, so what happened? Okay, Pawisha, are you with Professor Juan?
No, Professor Blin, we am at the seminar room. I think he is in his office.
Okay. So do you want to check him up?
Okay.
Sorry, I am.
Okay.
I am here again. Okay. Sorry. Okay. Second. Last result. Yes. Here. Last result. Yes. I was talking about try to reproduce the result.
Okay. So the sound is off again, right? Professor Juan, you are not connecting to an audio. He's talking, but we cannot hear. This is not the good. Not hear you. You are not connected to an audio.
Actually, I think his microphone is not working.
Yeah, I think
because
so.
I can see
Microphone symbol.
only microphone is disappeared.
Yeah.
Maybe it's about the installing or starting the Zoom session.
Pawisha, can you inform? Oh, his microphone is.
Sorry.
Oh.
Sorry. Can you listen me?
Yeah,
Yes.
Sorry, I thought that. Sorry very much for problem. I have many problem today. I don't understand. Sorry
No problem,
very
no
much.
problem. Don't worry, don't worry.
Yes, please. Next slide. Sorry. Okay, we have two examples for illustrate this theorem. Yes, yes. We can see that this point set is closest using the theorem. Yes. Next one. Okay, I want to go to conclusion future scope, please. Yes. Okay. As I say, Greve initiated the study of Banach contraction and facet-metric space, but it's not appropriate for metric Banach contraction translation. Gregory and Veremi solved this problem, introducing a new facet-metric space, now called GV facet-metric space. Many also try to translate problem from metric space to facet-metric space. Please. New slide. Yes. Caristi first point result. We can translate this theorem. Bassi proved this with an Archimedean norm. The first problem that we can try to prove if the Bassi theorem is remain true if we use a general T-norm. At the beginning of the talk, I said that Banach and Cannon contraction can be written as in charistic way. We have the same question here, not solved. First, can we rewrite facet contraction as a basic contraction? And a more difficult one, what about the facet Cannon contraction? Nowadays, there are in papers some definition of Cannon contraction in facet-metric space, but very, in my opinion, not natural way to definition. It's interesting to study this problem in facet Cannon contraction. Please, Juan. Author and thus present very interesting idea of fifth circle. Follow with this direction, we introduce the notion of fifth circle in facet setting. And we want to try to prove if our theorem remains true in the case that non-Archimedean facet-metric is replaced by general facet-metric. New one. Moreover, we present a result about the closeness of the fifth point set in facet quasi-knotted spacing mapping. And our result can be considered as an extension of fifth circle theory and quasi-knotted spacing mapping in the setting of facet-metric space. But it's possible to generalize Jauja theorem in the setting of facet-metric space. This is the second. I am talking in the second. It's possible to consider a set A and to construct a continuous mapping such that the A is the first point of this new mapping. Yes. This is the final consideration. Thank you very much. Sorry very much for my problem with the computer. Thank you for the invitation. Please, question or comment. Well, no. Yes.
Okay, thank you very much, Professor Juan. Please, any questions? Should be a quick one.
I have a comment, actually.
Please,
Do you hear me, Juan?
Yes, yes, yes.
Well, my feeling is that this circle, fixed point circle problem should be related or could be approached by the theory of multi-valued mappings. It is my feeling. So, because circle is a set. So if we consider multi-valued mappings, a set is a fixed point of a multi-valued mapping.
Yes.
And I'm curious if considering such an approach, okay, it's just a suggestion.
That's
because
very
it
interesting.
seems to be rather natural to consider multi-valued instead of single-valued mappings. I mean, we can associate to a single-valued map a multi-valued map, and the value is just the set of the consisting in the point Tx. So
you are talking about you are talking in metric space, yes?
Yes, in any setting.
Yes, it's very
metric
interesting.
Space or fuzzy metric space. I'm talking about the definition of the map. So maybe if we consider instead of single valued T defined on X with values in X, to define T as a multi-valued, formally as a multi-valued map, T defined of X, and the values are in the set P of X.
Yes, it's very interesting idea.
And just to think about this, it's a kind of suggestion.